let's continue on from where we left off in the last lecture, where we were sort of midway through the heap sort. And after that, we will go on to chapter 9 of the book, which is on order statistics and the selection problem. And that's not going to be very long, so hopefully we should be able to pretty much be done with that today. So quick review of the procedures that we had, which led up to the heap sort, which will lead up to the heap sort algorithm. So the first procedure was the max heapify, or simply heapify. And that was taking log n operations and would take any element in the heap and would sort of do a bubble down operation. It would make sure that the heap is maintained. And then we had some of the calculations, which, oh great, for some reason the thing is getting battery, so I hope people can hear me in the back. Can people hear me, or do you want me to speak a little louder? Are you okay with that? Yes? Okay, good. So we spoke about we did some calculations on the running time for max heapify, which was perhaps a little tricky and not so obvious, because the obvious solution seemed to indicate that it would give you a different solution. Sorry, not for the max heapify. Max heapify was fairly easy, but in terms of the build max heap was a little tricky, and we saw that the complexity was in fact linear. In other words, if you took a bunch of numbers which were unsorted and you created a heap out of that, then it turns out that the complexity is linear, all right? And why exactly is that? And this will be an interesting question when we get to the actual heap sort algorithm in a few minutes. And you should try to see, compare these two algorithms, the build heap and the heap sort, okay? They're doing fairly similar kind of things, but their complexity is different. Now, you may want to scratch your head and try to see why that is the case. It's not that obvious. And we mentioned this in the last lecture as well, that depending on exactly the algorithm that you're working on, the complexity can be different, okay? So in this case, we saw that the complexity is going to be shown to be, we almost got there, to be linear. So I think this is pretty much where we stopped. And we said, well, the cost of the build max heap is essentially the cost of heapify for a single node at a certain height, okay, multiplied by the number of nodes at that particular height, okay? So the number of nodes at that particular height was roughly n divided by 2 to the power h. And we saw this over here. So as the height is going from, let's say, 0 to 1 to 2, you can see that the number of nodes is actually reducing. All right. So the number of nodes over here at this level could be actually n. Over here it could be n upon 2. This would be n upon 4 and n upon 8 and so on. Okay. So it's inversely proportional to h, to actually 2 to the power h, okay? And so the number of nodes at a particular height is inversely proportional to 2 to the power h, and the cost of heapifying at a particular height we've already seen is O of h, okay? And that was derived from it being log of n, and we saw that log of n and h are proportional. So this was essentially the equation that we had. And so this was where we stopped in the last lecture. And I said, well, can we try to sort of figure out what is, just by looking at it, can we figure out what its complexity is? And we got an answer, interestingly, which said that, well, I know the answer is linear, so it's O of n. But can now we sort of go beyond that, go past that and see, can you sort of intuitively see why this should be a constant over here? Okay, because in order for this expression to be linear, for build max heap to be linear in n, we've already got an n over here, okay, which simply comes out. And then you've got an expression which is essentially h. O of h can be represented as h divided by 2 to the power h. And we're summing over, a bunch of values of h going from 0 until, some large number. In this case, it's log n, but it could be larger as well, okay? And can somebody try to justify why this perhaps should be a constant, O of constant? Can you just look at it and have an intuitive feeling as to why this could be constant? Yes. Okay, so you can think of it as geometric series, but it's not exactly geometric. That's an h, by the way, not an n. Okay, so you see that there in the numerator you also have an h, and in the denominator you have an expression which looks like a geometric series. So you're sort of right, but not exactly right. Okay, so so any intuitive feelings as to why this should be? Well, if h wasn't there, if the numerator h wasn't there, then it's clearly a geometric series, and that is easy to solve. Okay, but now you have a numerator which is also increasing. Okay, so essentially you have something like 1 upon 2 plus 2 upon 2 squared plus 3 upon 2 cubed, if I've got that right, and so on. So it's not clear that the denominator will clearly become very large, but there's a numerator as well over here, which sort of indicates that maybe it's constant, maybe it's not. But we know that it's a constant, so I'm just telling you, because Kyle already said that last time. Okay, so but why? And intuitive feelings. Yeah, but would that always be true if the denominator was increasing greater than the numerator? Would it always be the case? So what if I had 1 upon 2 plus 1 upon 3 plus 1 upon 4 and so on? Now I could make the statement that the denominator is increasing, the numerator is not, but is this converging? Is this constant? Is it independent of n, let's say? This is, which series is this? So you've basically got the right idea, okay? But a little bit more intuition is that 2 to the power h is an extremely, it's an exponential function. It's a very bad, in terms of h, it's going up really fast, and you've done this, right? So you've seen, you've got examples of how you can compare different algorithms. So 2 to the power h is one of the really fast-growing algorithms, in terms of complexity, in terms of h, it's extremely fast-growing, okay? So just to give you an intuitive feeling that h and 2 to the power h are, very different. And because 2 to the power h is growing extremely fast as compared to h, then you can sort of be able to see that, yes, this is probably going to end up with a constant, okay? So we can do some math on it. It's always nice to get the math under your belt. So if you just look at this expression, we could even take this up to infinity. Okay, so let's just forget about log n. We're going to change the exponent to be the sum going up from h is equal to 0 till infinity. And now you've got this expression, okay? And some of you might have seen this before. This is an interesting equation which comes up quite often in different, maybe in calculus, but a lot of applications have this equation. And this is given as one of the solutions to this, but does anybody know how to crack this? How would you actually do this summation k x power k? So it's a geometric series multiplied by k. Has anyone done this before in calculus? You should have. It's a very popular. It comes up a lot in different types of algorithms. So does differentials remind anybody? So if you take the differential of x power k, what do you get? You get k x power k minus 1, right? So now this is sort of looking like the expression that we have, right? If you look at this expression, k x power k, and this expression, the only difference is that it has one less power of x, so you could have an x outside over here, and that would result in exactly the same expression, okay? But then the question is, how does differentials help in doing the summation? So none of you have come across this before? Okay, I would have thought that perhaps you might have, but let me just show you how this could be done. So differentials and summations can be interchanged. Okay, that's one of the nice things to know. So if you have a summation over here with respect to, let's say, k, all right, so what you could do is, sorry, in this case, yeah, so what you could do is you could interchange the derivative to be outside, and you could have x to the power k upon k. And now you can solve this because this is a geometric series. That's 1 upon 1 minus x. And if you take the differential of this, that's 1 upon 1 minus x the whole squared. And then you have x in the numerator, and that's how you get this. Okay, so I just thought it's a neat thing to know, and perhaps you'll come across this again. So anyway, if you use this equation, you can simply see that the solution comes out to be a constant. Okay. So essentially, we've shown that your overall time in building the heap is actually n, is proportional to n. Okay, because this particular expression, as we saw, has a denominator which is growing very rapidly. Okay, and this becomes a constant. So that's where we are. We've essentially found out that max heap phi is O of log n or O of h, and build max heap is now constant in linear in n. Okay, so the next thing that we need to do is look at the actual heap sort algorithm. Okay, so now the question is, how could we sort this input array? We've been able to use build max heap, and we have been able to take an array. Let's say this is an input array which is unsorted. We've been able to convert it into a max heap. Okay, so now 16 is at the top, and it's bigger than its children, and so on, has the heap properties. So now, once you know that you have these two procedures, one which can create a heap, and another which can do heapify to any element in log n time. Now the question is, can you use those two procedures to be able to actually create a sorting algorithm? And it would be nice if it's stable, if it'd be nice if it's in place. But let's just think about, and think about the array itself. So this is just the representation as a tree form. But essentially what we're saying is we have an array, okay? We can convert it into a heap, and we can also do heapify on any particular element if necessary, okay? So what could be a good sorting algorithm to use? And the hint is that we're definitely going to use those two procedures, okay? Somebody else? Anybody? Any thoughts? How could you apply? How could you convert this into a sorting algorithm? Okay, so just think about it. We know how to convert this into a heap, and what does the heap essentially have? The main property of the heap is that it's a max heap, so it's got the largest number at the top, right? And you can, and even if the largest number is not at the top, and if it somehow got changed, you could still convert it into a heap in log of n time. Okay, so now are you getting any ideas about how to, and you try to convert that into a sorted array? So let's say you start with picking the largest number. Okay, so you may want to pick the largest number and put it somewhere, and so on. Okay, so yes. Okay, that's pretty good. So if I followed you right, you said that what we could do is, let's say we take the largest element, okay, and we say, well, we found the largest element, so now we know that this could go at the end of the array, because we're trying to convert it into non-decreasing numbers, so they're sort of increasing. Okay, so if you have this number and you convert it into a heap, so essentially we're saying that 16 is now going to be right at the beginning, and you're going to have a bunch of numbers which are going to be smaller than 16. And then what you could do is perhaps take that, put it into a separate array, and 16 would go right at the end. Okay, and then what you could do is replace 16, you said, with the second largest number. Okay, so what you could do is replace that with 14 over here, and then you could apply heap sort again on it. Okay, so that's pretty good. Can I get your name? Bharat. So Bharat's algorithm is there. Now, can somebody, if nobody else, and Kyle can give me perhaps another thought on it, can we do, is this about as good as you can get? And I mentioned a few other things. Can we do it in place? Can we make it stable? Perhaps, I don't know. Can you think of slight modifications to Bharat's algorithm and maybe make it have some nice features as well? So you're suggesting that we need to create an array, so it's taking up additional space. So that's not in place anymore. Okay, does it really need to be? Can we convert it into an algorithm, a sorting algorithm, which is in place? Now, you also said that you're taking the second largest number and putting it up here, which sort of indicates that now you've got to apply max heap or heapify on each one of those. Okay, but you've also got the problem that we didn't like earlier, is that you're creating a hole. Okay. And creating holes, if you remember, can result in this being not complete. Okay, so you could eventually have a hole over here, which would mean that this is not a complete binary tree. And remember, the complete binary tree was required if you want to use arrays to depict a heap. So you have a few problems, a couple of problems, right? One is that you're taking additional space. The second is you're replacing it with the second largest number, which is creating a few problems. Kyle, did you have better solution? Right, so I guess you at one shot have fixed both the problems. So basically what you're saying is that instead of replacing it with the second largest number, which is not really required, because we know that you could replace it with any number, and then you could do a heapify on that. Okay, and it will take just as much time, and it will also have the nice property that the entire heap will still be a complete tree. Okay, and then the other suggestion is that because now you have a heap and sort of an array, which actually has slightly smaller size, now you can put the 16, the largest number, right over there. So it sort of solves both the problems. Great. Okay, so we don't need to have an additional array. What you could do is you could take, so what would you do first? Kyle, could you repeat your algorithm again? Hold on, where are you putting 16? Okay, so you're swapping the last and the first, okay? So one comes up here, and then you're going to do the bubble down, which will essentially make it into a heap. And you would get a new number, presumably 14 would come up here, and it would still be a heap. And now you can simply do a recursive solution on that, right? And then you would eventually get, let's say, 14 over here. And this would be the second, then you would swap 14 with the second largest number so far, or rather the number that's right at the end of the array. You would swap these two. 14 would come over here, and then you would keep on repeating. Okay, so that's great. Can everybody see that that solved both the problems? Now, is it in place? Clearly, it's in place because you're not using any extra space, which is not proportional to n. It doesn't depend on. We take extra space, and if it's constant, that's fine. But if it's has anything to do with n, then it's taking additional space. Okay, and it's no longer constant in space. Would this be stable? Any thoughts on that? Would this be stable? In other words, if you had two numbers and, well, so far we've assumed there's distinct, so it's a bit tricky question, but there's nothing that we're looking at which is sort of indicating that it's going to be stable, right? So if you guess that it's not stable, then that's going in the right direction. Okay, so it's going to be in place, and it's not going to be stable. It's been shown that it's not stable. Okay, but without going to all the details, I can just tell you that. So let's just take a look at what we just mentioned, what Kyle just said. And first of all, what we're going to do is initially we start off with an array which is unsorted. Okay, and so we have to convert it into a heap. So that's where we start off. So we build the max heap, and that's going to be linear in time. Is that coming from outside again? I guess so. So this is going to take a time which is linear in n. All right, and then we're going to exchange a1 with ai, and where I starts from n. So we've swapped these two guys. Okay, so we've taken 1 and we've put 1 over here, and 16 comes down here, and then we do a heapify, and as you can see, well, 14 would clearly come up here, then 1 would go down here, 1 would get replaced with 8, and then with 4. Okay, so you can see 4 moving up and 8 moving in place of 14, and that's where you have. So so this is what you get at the end of each loop. All right, so as soon as you're done with this loop, this is the new heap that you're going to see, and you're going to have the heap slightly reduced, okay, reduced by 1, because now this is in its final position inside the sorting algorithm, and now you simply need to sort. You simply need to sort on this portion. Okay, so every time you do, you exchange your heap size decrements by 1. And then you do a max heapify. Okay, so every time the heap looks at a the sorting algorithm looks at a slightly smaller array. So eventually you can see that it's going to get all the way down up till here. And so that looks pretty good. And now the question is, if you think about the algorithm, does it seem somewhat similar to the build heap? Right, so in the build heap, we were sort of doing each operation. Each operation was taking order of log n, and we're repeating it certain number of times, which is proportional to n, right? And our initial guess was that it's going to be an intuitive guess was that it's going to be, well, maybe not intuitive, but the loose approximation was that it was going to be n log n. But then we went through a lot of fancy math, and we were able to show that it's actually linear. All right, unless we made some mistakes in the math, it seems like somehow that was linear. But now, can we have a linear sorting algorithm which is based on comparisons? Can we do sorting in linear time using a comparison-based algorithm, which clearly this is a comparison-based algorithm. It's not like bucket sort or radix sorting, things like that. So now we sort of, can you see the problem? It seems like this algorithm is very similar to build heap. Okay, because you can see that max heapify is taking log n time, okay? And you're repeating this n times, okay? So it's sort of very similar. And if you look at the complexities, we've got something very similar. And if I go back to what we did earlier, which was this particular slide, where we said, well, we're essentially doing the same thing, okay? But now the contradiction comes in that if it's a comparison-based algorithm, how can it actually be in linear time? So clearly, one of those not going to work, right? Which one do you think it is? Is this going to be linear in time or n log n time? Well, I've given you the answer, I guess. All right, so this is what your obvious solution is. Okay, but why is this not? Why can't you use the same analysis that you used in build heap to show that this is linear in time? So clearly, we've got a lower bound. I mean, we spent some time doing the lower bound. So we already know that the lower bound for comparison sorts is order of n log n. So once we have that, we can sort of say, well, it's a waste of time to actually try to show that this algorithm is very similar to the build heap, and you can do it in linear times because that's not going to happen, okay? Now, perhaps you can do a little bit of research and try to figure this out. That might be worth a research paper, okay? But the short answer is that there are some differences, okay? If you look at the differences, well, one of the differences that if we go back to the earlier algorithm, what were one of the main differences between the build heap? If I can find that, yeah. So if we did the build heap, where were we starting from? Yeah. I don't think I've got that particular slide anymore, but if you think back and you think about the differences between build heap and heap sort, can you sort of justify why it could possibly be one of them is linear in time, the other one is n log n? Any thoughts on that? Yes. Yes, so that could be one of the reasons. I'm not saying that I have a solid answer for you, okay? But I'm just pointing out that there are differences, okay? In one, you're going in from one direction to the other, okay? So in the build heap, you're actually taking the first node from the bottom, which does not have a child, okay? And you're doing heapify on that, and then you're going upwards, right? In this particular case, you're taking the largest number, you're swapping it with the number at the end, and then you're doing a heap. So you're doing heapify going downwards. Okay, so that's one difference. What was perhaps another difference? How many operations did we have to perform on the build heap versus in heap sort? So in heap sort, we clearly doing, we're swapping n or n minus 1 approximately n times, okay? Because you're taking 16, you're putting it at the end, and then we're doing the build, doing the heapify again and again. So we're going through all of the numbers, right? But in the build heap, did we have to go through all of them? Did we have to start right from the bottom? No, we didn't. Why? Because half of the numbers perhaps were right at the leaf, okay? And they didn't need any, if you already heaped, those last numbers already heaped their leaves. And so you started somewhere at the second lowest level, okay? So the range of operations was also different, okay? Those are perhaps two indications that the solutions are not going to be the same. But it's worth thinking about a lot more as to why there's a difference. But as I said, at the end of it, we do have a lower bound which says that any comparative based algorithm is going to take n log n. So we know that there's nothing wrong with our math over here. at least as far as deep sort is concerned. We can just rest on the fact that it takes n-1 calls, and each one of them is taking log n, so it's simply going to be n times log n. Okay. So that's essentially where we are, and we've already seen that it's in place, and I've sort of convinced you that it's not stable, perhaps. So these are the three the procedures. There's max heapify, order of log n, build heap, which takes linear time, and then heap sort, which takes order of n log n time. Okay, so that's sort of a summary of the heap chapter. Now, just as on priority queues, so this sort of revision for those of you who remember, we did priority queues in Q10 as well. So why do you think priority queues are particularly relevant when we start speaking about heaps? Okay. Now, I hope you remember what a priority queue is. What you have is you've got, let's say, a bunch of numbers, and you simply want to have them, go in. If you just have a normal queue, you just want to serve them in the order that they came in. So you have first in, first out. But in the priority queue, you essentially want to have these numbers sorted so that you have the highest priority being served first. Okay. So why do you think priority queues and heaps are sort of spoken together? Why are heaps a particularly good data structure for use of priority queues? And when you want to answer that, you want to think about, well, if you're looking at a priority queue, what were the typical operations that you wanted? Did you need to sort the entire priority queue? Let's say you have 100 patients, okay? And you want to, you want to serve the patient with the highest priority first, okay? Does everybody need to be sorted? Doesn't, right? You just need to know, well, who is the next patient? And the next patient is simply the one who has the highest priority, okay? You just need to pick the highest priority, serve that particular patient, and then you can, as long as you can figure out who the patient is or which number has the highest priority, you don't need to sort the entire, all the patients or all the numbers, at one time. So that's why heaps are particularly useful, okay, when you talk about priority queues. And this should hopefully be, a reminder to you that we hope other students also covered this in 210. But priority queues are very, usefully implemented using heaps, simply because the two operations that you want to do is insert and delete. Okay, you don't want to do sort. So if you don't want to do sort, all you need to do is insert and delete, and we've already seen that both of these operations can be performed in log n time. If you're doing insert, you simply insert, and then you do the bubble up or bubble down, and the same thing goes in deletes. Okay, so that was sort of a quick, hopefully a revision for those of you who remember priority queues, or those who haven't. Okay, so that sort of finishes the chapter on, and we now go to the which is order statistics, and also referred to as the selection problem. Okay. So what do we mean by order statistics? Well, the following is the definition of the ith order statistic. Okay, and it's very simply, it means the ith smallest element of a set of n elements. Okay, so when you're saying the first order statistic, that simply means the minimum. Okay, if you're saying an nth order statistic, that simply means getting the maximum out of n numbers. All right, and the median would be the halfway point. So you can imagine that having order statistics can be useful. Okay, for example, if people want to know what is the mean in your midterm, you may not necessarily want to have the entire data sorted. All you need to know is the mean. Okay, and if you want to know the mean, then the question is, what could be an algorithm to actually just get you the middle value? Okay, or maybe if you're not looking at just the middle value, you're looking at some other value, maybe n upon 3, for example. Okay, so the question is, how could we do that? Can you think of an algorithm which all the algorithms that we've already studied? Can we use any of those existing algorithms? And if we did, what kind of complexity would we have? Okay, so we could start off by talking about the minimum and the maximum, and then talk about the median. So any thoughts? What would be the complexity of getting the minimum of n numbers? It should be straightforward, right? So you have a bunch of n numbers. You just want to get the minimum or the maximum. Yeah, that would simply be linear. You just take, go through all of the elements, and you keep track of which is the smallest or the largest. Okay, so that's fairly a linear time algorithm. How about median? And do you think it would be linear in time, or it would be something a little bit more complex than linear? Carl, you're nodding your head quite strongly. Why? Okay, so you could partition it and get the top k elements in linear time. Okay, but you don't have an intuitive feeling as to what the algorithm was about. I mean, how did you actually do it? Any other thoughts? I mean, so Kyle has a suggestion that, well, he says that it should be linear, right? But what's a nonlinear algorithm that we could use, Logan? Yeah. Okay, that's interesting thought. You could use a heap sort to find, that would be interesting. I mean, you could think about how one could use heap sort, and that seems to be fresh in our minds, and that maybe that's why it could be relevant. But you want to be very specific as to, so in a heap, if you look at the heap is not sure. The heap is essentially giving you, the highest, the largest number at the top, all right? And it's sort of telling you that you have half the other numbers on one side and maybe half on the other side. But if you remember, we looked at the worst case. We saw that the largest side could actually be 2/3 of the smaller side. All right, you remember that? Spend a few minutes on that. So if it's a 2/3 to 1/3 ratio, then it may not necessarily work. All right, so it may not necessarily work, but it's a good thought. And it would be interesting to see if you can actually use that algorithm to figure out a way to solve it. Okay, because obviously everybody, algorithms, people come up with new algorithms all the time. It doesn't necessarily mean that this is the algorithm. Most likely it is the best, but one could come up with new algorithms. I mean, it's a research area for sure. So, so just a little definition. If you have n which is even, then we define median to be the lower median. Okay, so it's something for you to know. And Logan just mentioned very accurately that if you just used sorting algorithm, then you could just sort it out and then find the nth element in fixed time, simply because it's an array. Okay, and you could just go to the nth index of that particular array, and you could do that in constant time, and you could do the sorting in n log n time. Okay, so the complexity would certainly be order of n log n, but as we know that there has to be a better way. Okay, and some people already know that there is a better way. They don't remember how. Okay, so let's try to think about how could we actually use on the existing algorithms. And so, so we've talked about merge sort, we've talked about quick sort. Okay, now so I'm sort of focusing in on a couple of algorithms. And now, which one of those do you think you could use? All right. So those are two powerful algorithms. Both of them work in n log n time. All right. They both have nice properties. So which of those two algorithms do you think would be perhaps a better choice for getting the nth order statistic? Now something is coming back, right? but which one? Yes. Okay, so you're popping the heap n times. And so what's the complexity of that going to be? Is it going to be linear? So it's going to be, because popping requires a log n operation as well, right? So you're back to sort of like an n log n, because you're trying to get midway to the median, and that's going to take n upon 2 operations, and each operation is going to take log of n time. So it's sort of like sorting, except now you're sorting halfway. So you're back to the original problem. So heaps are not working out, right? So now I've already suggested that let's think about divide and conquer. Okay, so the two divide and conquer algorithms that I mentioned was merge sort versus quick sort. Okay, now think about which one of those two would perhaps be better at solving. You're trying to get somewhere in the middle. All right, so which one of those two could be perhaps better? Any thoughts on quick sort versus merge sort? Now remember how did quick sort work? Quick sort said, well, depending on whether you're using the randomized version or non-randomized, it basically said that we're going to take a pivot element. Okay, let's say the pivot, it's non-randomized. You take the pivot element, and then you find out, then you do the partition. And what the partition does is actually it places the pivot in the right location, and everything to the left of the pivot is smaller than the pivot, and everything to the right of the pivot is larger than the pivot. Okay, and the pivot comes out to be in the right location inside that array. So does that give you any ideas? Yes. Yeah. Right. So essentially what you're saying is that you could use quick sort, and quick sort was basically sorting the entire thing, right? And you said that you could do quick sort. You find do the partition. Okay. The partition gives you the pivot that you've selected. It tells you exactly which location it is in, right? So if you remember the partition algorithm, what it did was it gave you the index of the pivot. Okay, so now you already know the rank or the location of the pivot. So if it's like in the middle, you know that that's the median. All right. So just by doing the partitioning, you could actually get the median. But what if it's not in the middle, right? Then you could look at the left side. If you're looking for, let's say, the third element, and the pivot's location is 5, then you look on the left side, and vice versa. Okay, but you don't necessarily need to do the quick sort. Okay, you mentioned quick sort. Why would you not need to do the entire quick sort? And how is quick sort now going to be different from our new algorithm? So you've got the right idea, but you said something slightly incorrect. Yeah, you don't have to do it on both sides, right? Because all you need to do is figure out whether you're looking for a particular element, and you're saying, well, is that element element to the left of the pivot or to the right of the pivot? Okay, and so your recursive solution, your recurrence relationship, earlier we had a 2 in it. Okay, so is this going to continue to have 2 in it? If you think about the recurrence relation, in quick sort, we said, well, T of n is at best going to be 2 times T upon n upon 2 plus partitioning time, which was order of n. Okay, so now it's not going to have 2 simply because, can I get your name, sorry? Sorry, Isaiah. Okay, so Isaiah's suggestion is that we're going to be using sort of a simpler version of quicksort, but we're not going to apply it on both sides. We're only going to look at the left or the right. And so perhaps the recurrence relation is going to change a little bit. And then we can use our master method to figure out, in the best or in the best case, what it's going to be. So let's take a look at the actual algorithm. And before we get to that, let's just take a minute to look at the minimum or maximum algorithm. So this is fairly straightforward. But I'm going to spend a minute on it because I want to do something interesting with this as well. So let's say you have, you set minimum set up to be the first element, and then you keep going through the entire array. And if minimum is greater than or a sub I is less than, then you simply swap, okay, or simply set minimum to the new value. So this seems to be a fairly straightforward algorithm, as I think Logan, you mentioned that this is going to take linear time, and the same thing can be done in maximum time. However, because probability is something that I think you guys are not, well, you haven't taken the course, and probability is coming in very frequently over here. I don't know why they don't have probability as a prerequisite for this course, honestly, okay? I'm going to recommend that to the academic committee. But which means that you would normally take this course, maybe not in your junior year, but after you've done the probability course. That way, a lot of the algorithms would actually become a lot easier for you after you've taken the course probability. But here's another probability question, just so that you build up on your probability. How many times do we expect line 4 to be executed? Okay, so this is a linear time algorithm, right? But what I'm saying is that the number of comparisons is clearly going to be linear, but how many times is the minimum value going to get revised? Okay, sort of like, remember the hiring problem? So sort of similar to that. How many times are you going to hire a new person? How many times are you going to update the minimum value? It's an interesting problem. It's an interesting probability problem. So any thoughts on that? How would you go about doing this? So the first thing that you do whenever you have a probability problem is what? You define a random variable, which is a, what do you do? Indicator random variables. All right, just remember that. Whenever you have a probability problem, at least as far as this course is concerned, your first step is try to figure out an indicator random variable which could help you. Okay, so here we're going to set x sub I, and half the problem is actually figuring out what the indicator random variable should be. Okay, but let's say in this particular case, we take x sub I to be the indicator random variable for the event that the line 4 is executed in the ith iteration. Okay, so you're going from I is equal to 2 to n. Okay, and you're checking whether the previous values of A were actually bigger than or smaller than the new value of min. Okay, so you're doing that comparison. So the question is, what would be, do you think the number of times that min would be updated would also be linear, or should it be less than linear, or should it be more than linear? So you have a whole bunch of random numbers, right? They're uniformly distributed, presumably, okay? And you have the number 10, 5, 3, whatever, and then you select a number and you make it the minimum, right? Now you're comparing it with the next number, and you're only going to set it to be the minimum if the next number is bigger, is smaller than the current minimum, okay? So do you get the feeling that this is not going to be linear in n? Or do you think it's going to be, are you going to do something like n upon 2 or something which is linear in n? It's a tricky question, but think about x sub I, okay? So what is the, if you think about the probability that that x sub I has, well, let's think about this. Well, first of all, x is going to be a summation of x sub i's, okay, because it's a random, it's an indicator random variable, okay. That's always the case because x sub I is only going to have one value, okay. All the rest are going to be 0, okay. And now I don't want to spend too much time on this, but think about this. The expected value of x sub I is actually going to be 1 upon I. Okay, and this is simply the property that a sub I is smaller than all of the previous values, and they're uniformly distributed. So the probability that a number is smaller than all the previous values, and there are I values, is simply 1 upon I. Okay, let me repeat that. You have I random numbers, and I'm saying what is the probability that a particular number is the smallest? Since they're all uniformly distributed, the probability should be 1 upon I. Okay. And once you have that, then you have again a series which is simply a summation of 1 upon I, and we've seen that before. That comes out to be log of n. Okay, so it's not linear in n; it's actually logarithmic in n, which sort of makes sense as well, because you can imagine that you might have a number, you've picked a minimum number, but then the chances that you find another minimum number become smaller and smaller. Okay. Anyway, so that was, I thought, was an interesting problem that that could come in handy when it comes to solving probability problems. So now let's think about the problem that we just said. Well, we said we're going to use quicksort, and quicksort, just as a revision for those of you who've forgotten, is as follows. So we have an array going from P to R. So P to R, okay? And in the non-randomized version of quicksort, we take R to be the last element. We take the pivot to be the last element. So we use this as a pivot, okay? And the partition function, what that would return is it would simply return another array, and it would place the pivot such that everything to the left of the pivot was less than the pivot's value, and everything to the right was greater than the pivot's value. They're all distinct, okay? So that's just the quicksort algorithm, okay? Hopefully you remember that. So now if you're using quicksort and you remember that the partition actually returns you the index of the pivot, we already know that the partition takes theta of n. We already saw this. The recurrence relation was T of n in the best case for quicksort was that it divided up the array into equal parts, okay? And if it was dividing it up into equal parts, then we had, in the best case, 2 times Tn upon 2 plus the partitioning time, which was theta of n, okay? And this we know from a whole bunch of techniques. We know that that is n log n, okay? But as Isaiah, sure, yeah, I got that name right. So as I just pointed out, that this is now going to change to 1, right? Because we don't want to do, we don't want to do sorting. All we need to do is somehow look at either the left side or the right side, okay? So if you're getting the index of the pivot, all right, then, and if you're looking for the nth smallest element, we can simply say, well, how does the index of the pivot compare to the number, the statistic that we're looking for, okay? And if it's going to be either, the number that we're looking for is going to be either on the left side of the pivot or the right side of the pivot. The pivot has been positioned in the correct location, okay? And that's what partition does. So, so this essentially is going to become 1. And so if you have a very, roughly speaking, without going through in-depth analysis, which perhaps we will get to, if we look at this recurrence relation and you replace 2 with a 1, what does your theory tell you? What would be the order of complexity? So you would have T of n is equal to T upon n upon 2 in the best case plus theta of n. Which case is this for the master method? And just looking at it, can you perhaps tell me what the answer is going to be? clearly it's going to be, this is, if you compare this to the f function, you can see that now a is 1 over here. And so this is log of a to the base b, which is log of 1 to some base b, and log of anything to the base b is equal to 0. So that's going to be n to the power 0. Okay, and n to the power 0 is a constant compared to this, so it's going to be theta of n. Okay, so that's just a quick look at Master's theorem. So, but we can also use the other methods such as the recursion tree. So now you can see that using quick sort, perhaps a slightly modified version of quick sort, you can actually get the nth order statistic in linear time. Okay, just by a very rough calculation. Okay, that we can see that the recurrence relation is no longer going to be twice as much. It's simply because you're going to either go look at the left subarray or the right subarray. Okay. But that was a very rough calculation. And of course, we're going to spend more time on trying to do a more detailed calculation. And this was just some reference slides, just in case you've forgotten quick sort. And this was the randomized. So we're going to use a randomized version of quick sort for this algorithm that we're going to propose. And this was a summary. So let's go forward. So the algorithm that we're going to use for the nth order statistic is called randomized select. Okay, why is it randomized select? Because it's going to use sort of some of the sub functions of the randomized quick sort. Okay, and which function it's going to use? It's going to use the partition function. Okay, and it's going to use the randomized partition version of quick sort. Okay, so here's how it works. Here's an example. So let's say that here's the array that you want to get the ith element out of. Okay, and so let's say that you call randomized select with 4 parameters, 4 arguments. You give it the array. You give it a lower index of the array, the upper index of the array. So in this case, it's starting from 1 and you're going up to 5. So P is equal to 1 and R is equal to 5, just like in quicksort. And now you're giving it one additional argument, and this argument is the statistic that you want. Okay, so in this example, I'm saying that I'm looking for the second smallest element in that array. Okay, now if we sort of work forward and say, well, let's assume that, just for ease of understanding, I've sorted this for you. And if you sort this, then you can clearly see that the second smallest element is 4. So essentially, this particular randomized select algorithm should, with these arguments, return you the number 4. Okay, why is that again? Because it's looking for the second smallest element, and we can see just by looking at this that the second smallest element is the number 4. Okay, because 2 is the smallest and this is nothing between them. So this is what we want. And now let's take a slightly closer look at an algorithm which will actually do this. So we had a rough idea how this would work, as I had mentioned that, but we actually need to have a detailed algorithm which actually solves this problem. Okay, so here's the structure of the algorithm, and what I'll try to do is go through this and let's see if you can understand this. Okay. So it's going to be a recursive algorithm. So it's going to call itself, as you can see, on the left side or the right side, depending on some variable. And before that, it's going to have some kind of conditions which will make sure that the recursion is going to end. So the first condition is that if P is equal to R, then clearly you've got to the end. Okay, so just to make sure that you guys are awake, what is it going to return when P is equal to R? What should it return? You've got an array, and P is equal to 1 in this case, but this is recursive. So at some point, P and R are going to be equal. So what should it return? If you simply want the element which is the element number 4 in this case, but the element which has the ith order statistic. So if P is equal to R, that means you just have both P and R are pointing to the same location. All right. Yes. Yeah. So yeah, you don't need to return an array. You actually here, if you look at it, it should return the number 4. Okay. So you're looking for the number, not the entire array. Okay. So you're almost right. So you essentially need to give it a sub something. All right. So you could simply give it P or R. Right. So that was the easy part. Now, let's think about what randomized partition does. So let's assume that you give the following array to randomized partition, which is taking P is equal to 1, R is equal to 5. And let's assume that because it's randomized partition, it's going to pick a random number. Okay, let's assume that that random number is 4. Okay, and this is again a revision of quicksort. So let's assume that the random number, the pivot is going to be the number 6. Okay, so what should Q be equal to? Q is now the return of the randomized partition function. So if you remember your randomized partition function, basically it's going to be returning you a particular value, which is going to be the value of the pivot. Okay, I think I mentioned that somewhere. So what should Q be equal to in this case? So what's the array? How is the array going to be now split up? So what we're saying that the random number is 4, okay? And so the partition function is going to place the pivot, which is 6, in the right location. And so 6 is, you can see that I've already done this for you. So 6 is going to be somewhere in the middle. All right. And there's going to be, so you can just use this and tell me what Q is going to be. So Q is going to be the index of the pivot, which is 3. Okay, so we've got so far so good. We've got Q is equal to the index of the pivot. Okay. Now we're setting K to be the number of elements in the left-hand side of the array. Okay, including the pivot. All right. So K is essentially now the pivot is right in the center. So K in this case is going to be simply equal to 3. And how are we going to calculate K? What should be the equation for calculating K? So we've got all of these values, P, R, and I. So what are we going to use to calculate the value of K? Starts from P, ends up at R, and you've got Q, which is 3. So not too difficult, I hope. We're just simply going to take Q minus P. So we want to take Q, the value of Q, and the value of P, which is 1 in this case. And we're going to add 1 because we want to get K to be equal to the number of elements over here. Okay, so fairly straightforward. Now, the next question is, what happens if I is equal to K? All right, so essentially we're saying that you're looking for the ith statistic, and K is now equal to I. So what are we going to do? Is that, now do we have the solution? If I is equal to K, essentially we're saying that we were looking for, let's suppose that we were looking for the 3rd order statistic, okay? And we found that I is equal to K. So essentially what we're saying is that we've already found the solution. The pivot value is the answer. All right. So hopefully you can see that. The next portion is, if the pivot is not the answer, then obviously you're looking for the ith statistic either on the left side or the right-hand side in the 2 sub-arrays. So let's assume that it is on the left side. Okay, you're looking for the ith statistic, and that is less than the position of the pivot. Okay, so how are you going to call randomized select? So you're clearly going to call it with the same array. Now, what are the values of P, R, and I going to be? Are those going to change? Yes. Yeah. So sorry, you said R would be set to the Q value? Okay, yeah. So this would be set to Q. I would be what? I would still be too big for the second order statistic. Okay. So any suggestions? Is this is almost correct, I would say? It's almost correct. Yeah. Yeah, R should be Q minus 1, right? Because you've already checked for this guy. And if that was the case, then you already have found the solution. So you can just reduce a little bit, okay? Just make the problem a little smaller. So that's what we have. You have P and Q minus 1 and I, okay? And the last case is, what if it's on the other side? In that case, what would AB, the arguments be? We're still giving it A. What would P be? And what would R be? And what would I be? So now it's on the other side. So clearly, it's somewhere over here. So what would the values of P, R, and I be? Yes? What about I? I would stay the same, okay? So P is clearly Q plus 1, okay? Because this was right over here. So we're looking at, just like before, we don't need to include the pivot value. So this is perfectly fine. We're going up to all the way over here. But is I going to remain the same? So remember, this is recursion, and it's taking on, it's saying that now I'm only going to be looking at this portion of the array. And I'm looking for, within that array, the ith order. Yeah, the new right side. So it has to remove all the elements that were on the left side. Yeah. So now, essentially what we're saying is that if we're looking for the number that, let's say the number that we were looking for was 7, for example, over here, then we're looking for not the, well, this would be a different example, but within that, we've got to subtract the value of I, to subtract that from K, okay? Because that's already has been figured out, okay? So in this case, I'm not sure if I missed a slide, but you would have, yeah, so you would have Q plus 1, R, and then I minus K, okay? Why are we subtracting K from it? Because these are all the elements which have to be excluded, because we've already got the K smallest elements already. And now the elements which are bigger than K are only there. So we have to take the I minus K smallest element from this subarray. Okay. So so that seemed to be okay. And this was an example where I is equal to 4. As you can see, let's suppose that we were looking for the 4th element and we found K to be 3. So in this case, you would use I minus K, or 4 minus 3, which would be 1 in this case. And so in this particular array, we're looking for the number 7. And so we would be looking for the smallest element on the right array, which would be 7. Okay, so hopefully you've been able to manage to follow me through these examples. So, so that's the actual algorithm, okay? And what I would suggest is, here's example in the book, and it gives you a much larger array, somewhat larger array. It gives you the initial values, and you can use this just to make sure that you understand this. Okay, so just work through this example, and it's shaded particular values inside the array which indicate where the pivot was. Okay, so I'm not going to spend too much time on this, but you can see that if you can't work out these numbers, I've worked out some examples over here, what Q is and K is. Just make sure that you can see. It's a little tricky. Just make sure that you can work through this example so that you know how this algorithm is working. Okay. Right. So we do have a few minutes left, and so let's start our average case analysis. We may not be able to finish it, but let's try to see how one would actually do the complexity analysis over here. Okay, so as we saw in the quicksort, in the randomized quicksort, the analysis was a little tricky, and it required expectations and probability distributions and so on. So we will generally use the same method. Okay, so how do we start? Whenever we have a probabilistic problem over here, as suggested a few minutes ago, we define random variables, and what do we do? Start with indicator random variables. Yeah, that's a good starting point. So we're going to define an indicator random variable, x sub k, for k between 1 and n. So you have an array going from a particular size, let's say from p to q. And we're saying that x sub k is the indicator random variable that p through q has exactly k elements. Okay, so in this particular case, we're essentially saying that you select a certain pivot. Okay, so the example was q was 3, which was the pivot, and we're saying that what is the probability? Well, we're defining the indicator random variable x sub k that the left side, including the pivot, has exactly k elements. Okay. So the next question is, what is the probability of x sub k? What is the probability? Yeah. So 1 upon, sorry, n. 1 upon n. Okay. Would people agree to that? So essentially, you can see that it's going to be 1 upon n. Why is that? Because we're picking the random number randomly, obviously, and it's uniformly distributed. So it's going, the probability that is going to be picked somewhere, anywhere, it's simply going to be 1 upon n. Okay. In this case, k was equal to 3, but you can imagine that if it was picked over the pivot was over here or over here, it would simply be 1 divided by the number of elements in that particular array. Okay. So the expected value of x sub k, remember that in indicator random variables, it's 0 times the probability that the event doesn't happen times 1 times the probability that it happens. So it generally comes out to be the same. So it's simply equal to the probability that that event took place.